Always a pleasure to be here. Good to see a lot of unfamiliar faces this time. I'm going to speak about NGS tens, and let me just find it here somewhere. Let's see. It's in GitHub, and I'll point out the repo. Okay, I think the documentation is here, and I'm going to go over notebooks, two notebooks that are here. That's the plan for the next half an hour. This repo was, the code in this repo was started essentially by Joachim, and he was visiting Portland at some point several years ago. And then many people have contributed to it, and you can see the contributors here, including Paul, who spoke before. The first build pipeline, I think, was Paul put it in place. And yesterday, Matthias revised the build pipeline to it's working. I can't say more than that. And the single largest contributor to this is Christoph Wintersteiger, who is here. Yes, he's there. Yes. And I am here to give you an invitation to this Tentpitching business. So it's a non-standard time marching scheme. So you could think of time marching schemes as time stepping from one constant t equals constant to next t equals constant, but that's not how we're going to proceed. The documentation here gives you notebooks, which I'm going to open. I hope to show you a live demo if I can find among all these windows. Geez, where this? No, this is not it. Could it be this? No. Sorry, just let me. There we go. I know this is for tomorrow. This one, good. Okay. So, should I make it bigger, maybe?
Full screen?
Works? Okay. Okay, so tent-shaped domains. We're talking about tent-shaped domains in space-time. Vertical direction is time. Horizontal direction is space. And the reason for that is very simple. Our basic underlying assumption is that we're trying to solve hyperbolic problems. So if you're not interested in hyperbolic problems, now would be a good time to step out or do other things. This assumption implies that there is a wave speed, a finite wave speed, and that furthermore implies that there is a light cone at every point in the space-time. For example, here there is a domain of dependence and a domain of influence that's a double cone, and that implies that you can think of a tent-like structure where you erect a tent pole in the space-time, vertical direction being time, and if your tent pole is not too high, then the domain of dependence, which depends on the propagation speed or the wave speed, that domain of dependence lies entirely within the tent, which means you can solve for the solution inside the space-time region with just data from here. If the tent is too high, like in the other picture, then the domain of dependence falls outside the tent, and you have no right to be able to solve that problem. So that's this constraint on the tent pole height is called a causality condition. It's different from the CFO condition, which comes from a discretization. This is before discretization. So that's the causality condition. So what we want when we want to try to solve using tents is an algorithm that will mesh the space-time using such tents in an unstructured way. And that's part of this repo, and also several methods to solve. So the notebook is structured so that this first notebook is just going to give you a sort of a high-level overview of what you can do, and then in the second notebook we'll get into a little bit more details on the methods to use. Okay, so Paul mentioned tent slab object. The tent slab object is the meshing object. So import NGSolve, and then from NGS tents you import a tent slab, and let's start with one dimension. You make a 1D spatial mesh, that's this code here, and then you ask the TenSlab object to give you a space-time mesh. So that will be 1 dimension plus 1 dimension. That will be a 2-dimensional mesh in the space-time. You have to give it a height of the slab that you want to create, and of course you have to set a maximal wave speed. If you don't have a hyperbolic problem, the wave speed doesn't make any sense. This is why I mentioned we're only focusing on the hyperbolic problems. Then you say pitch tens, and that creates a tent slab object TS, and you can draw it in 1D or 1 plus 1D. You don't need fancy web GUI for this. This is just matplotlib, and here is a space-time tense. So this is you can think of it also as an advancing layer. The blue layer has become the green layer, and the green layer has become the red layer, and is marching through in time. Okay, so this is a visualization of advancing fronts, and already you can kind of see some of the advantages of this type of method. For example, all the blue tents here, this sort of half triangle here, or triangle, is a tent you can solve independently of this, because you have data here using which you can solve here. You have data here which you can solve here. So that means all these blue tents can be processed in parallel. Then comes the green tents. Once you have the blue tents processed, you have the solution here, 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 here on the blue front. So you can solve this in completely in parallel to this. So these are small objects. Tents are small objects, so you can do thread parallelism using a concurrent queue. So here's a diagram of 10 dependencies. You can solve tens in this particular case 0, 2, and 1 simultaneously, and once you do that, then you proceed to the next level and solve the green tens, and then the next level, and so on. Okay. That's one advantage. The other advantage of this type of methods is that when you have small geometrical features in one part of the domain, you're forced to put small spatial elements, and because of the causality condition, you'll get automatic local time stepping. And to see that, we'll see more examples. We'll see more examples, but I'm just going to. This notebook tells you how to query various aspects of tens, given a tent, what are its neighboring tens, and what is its height, etc., etc. Very useful when you're trying to debug. Okay, now here's another mesh. We made up a mesh where there's a concentration of points near the space. It's a unit interval at the point 1, or near the point 1. There's more concentration of points, and then if you ask it to pitch tens, and then you ask you to draw the tens, you see that there is a lot more tens here, which shows you how local time stepping is automatically built into this algorithm. And if you have different wave speeds in different parts of the domain, that's another example. Here's an example where in the middle of the domain the wave speed is high. So you can see it has pitched tens where the height of the tent pole is lower here in order to accommodate the causality condition, whereas the height of the tent poles here is larger. Okay, so now you have a feeling of how, some of the advantages of this method. You can do the same thing in 2 dimensions and 3 dimensions. In 3 dimensions, I'm still waiting for Joachim to make a web GUI in 4 dimensions, so we can see. But okay, I'm sure you have ideas on that. So tomorrow, okay. So in 2 space dimensions, we can still draw pictures. We just have to go from 2 to 2 plus 1 dimension, so that'll be 3D. And here's an example, maybe an example of a wave equation. So this is a general form of a hyperbolic equation, and you have to provide the flux in order to define the hyperbolic system. For the wave equation, we would typically write the wave equation like this, but if you write it in a first order form with introducing the flux variable and a scalar variable, this is a standard rewriting of the wave equation, then this becomes a system like this, and it's a hyperbolic system where the flux is all of this. Okay, so it fits into into this first order hyperbolic setup that tens are made for. and we're going to solve this now on a somewhat cooked up domain. The domain is here. It's got tiny features here. You see. So we're forced to put tiny elements here because of constraints imposed by the geometry. And a wave comes in through this inlet and then goes out, and here we have larger elements. Okay, that's the domain. Okay, the next step is, this is a two-dimensional domain, so we're going to construct slabs of tens on top of this two-dimensional domain. And the algorithm as well as the code is uniform in dimension. I believe the dimension is a template parameter. Right? So basically, it's the same algorithm as the way we wrote it in the paper, and that's the implementation is also uniform in dimension. Okay, here is the tens lab, and then to report some characteristics of the created tens labs, and you can see a visualization right here of the pitched tens. If you rotate it, you'll see how, maybe I need to zoom in. You see tiny tens here, larger tens here, and here there's an argument up to level whatever. I think we can increase the levels, and you'll see more and more of the tens. Previously you had a single layer of tens, now you see further layers, and it fills up and makes up a space-time slab at the final level. Okay. Now let's solve the wave equation on this domain. For that, we need this submodule of conservation laws inside NGS tens, which contain things apart from meshing, like solvers. And we'll get more into it in the next notebook. But for now, let's just import a ready-made object called a wave solver. And it's for the moment it's a black box. I'm not telling you what, but it knows how to solve the wave equation. And if you have a hyperbolic conservation law that you want to solve, you can do it, but wait until the next notebook. So to the wave object, we provide the boundary conditions and the initials and the initial condition, and we ask it to solve. This solving happens through an explicit time stepper. So we know that we're marching tent by tent. There's also a marching within the tents. In other words, we're solving within each tent using an explicit time stepping. So we break up a tent like this into sort of sub-tents, and we have to tell the code, or the user has to specify how many sub-tents you want to break up a tent into. The more you break it up, the CFL condition within the tent gets better. So the number of sub-tents is like a CFL condition for explicit time stepping within a tent. Okay, and as with any other method, we don't precisely know the stability constants for a given problem, so we have to experiment to find out how many subtents we need. Okay, so here we are setting 10 subtents, and there's a particular type of time stepping that's very well suited for these tents that I don't think I would have time to talk about, but we've implemented that. And then we solve. We first provide the initial condition inside a grid function, and we ask the wave object to do propagation. One step of the propagation is finding the solution within one time slab, and then the next step it's going to fill up the same time slab, but placed at a higher time slice. Then we keep repeating the time slab over and over again. Okay, so maybe that went by too fast. There was. Did anybody see any propagation? Okay, I thought so. So that's why we've saved it, and we're gonna see it now better, like that, as an animation. You see how the pulse went through the inlet to the outside, and it begins to propagate. This is an animation built from the top of the 10 slabs. There are many 10 slabs. There's a whole space-time slab, and that which gets repeated many times, and we're just looking at the solution at the top of the tense labs. Okay, so this is what has been in this what I just spoke about in this notebook, and I haven't really talked about the methods underlying it, and I'll go to the next notebook. I think I still have 10 minutes or something. So let me do that. Okay. Okay. There is some technology that goes into the solvers, and tends look like great objects. I have the first notebook was an invitation to use tens. The one drawback of tens is that it is not a space-time. It's not a tensor product of space and time, and we're going to. Our methods are. We're approaching it from the point of view of fixing that drawback. So let me speak about that a little bit. The way to fix it is something called the mapped tent-pitching schemes, where we map a tent. This is not a tensor product domain. This is a typical tent. How do we fix it? We map it into a tensor product domain. The price to pay is that the map is singular, because these edges have blown up into these faces. So at the edges of the map, your Jacobian would be 0. Okay, but there exists such a map. And it's easy enough to just write it down. It looks like this. There's the space variable at the bottom has not changed. What has changed is the time variable. So time has become something twisted, something we call pseudo time, and the pseudo time is denoted by tau here. Okay. And the formulas are simple when you write them going from going this way. You know, they just look like this. You know, there's phi, the convex combination using the pseudo time. And then the key is we have to understand what happens to the equation under this transformation of variables. And there is this theorem or proposition or whatever you want to call it. So if this is the hyperbolic system you want to solve, then on the mapped domain, instead of solving this, you should solve this. So things have changed. Your d over dt has now a funny object with the geometry of the space-time inside here. This phi is a convex combination, phi top and phi bottom, the tent top and the tent bottom. So the geometry of the tent is inside the first d over dt. And then there is a delta here, which is the difference of the heights between the top and the bottom. So it kind of looks like a hyperbolic system. It has the same structure. So a lot of the methods that are suited for hyperbolic systems, like the DG method, can be carried over, except you have to keep track of these extra bits. And that's the method. That's the mapped Tentpitching method. Okay, how do we carry this over, and how is it implemented? Once I explain, if you want to use it, you need to know a little bit about what's under the hood, and that's how do we do a DG method on this. If we do a DG method on this, there are some numerical fluxes, and if you provide your own numerical fluxes, you have your own method for your hyperbolic problem, because you are now able to specify f. You're able to specify the numerical flux, and so you would have all the tools to solve your hyperbolic problem. So how do we give those things as inputs? NGSTens allows you to give you all of those as inputs. First thing is the f. Without the f, there's no hyperbolic problem, the flux. So you need the f. So you have to define f in a function, and then you pass this function to the constructor of a conservation law object. That's how the code is structured. So this little f, that's here. Now, when you design a DG method, what you do is integration by parts, which we do from finite element 101. So we integrate the divergence by parts. It became the gradient, and then there is this boundary term which we replace by numerical fluxes. Everybody has their favorite numerical fluxes. So we're not telling you what to use. We're just saying that you can provide that, what is in that parenthesis in a function. Okay. But then I should mention that the numerical fluxes on the interior facets are generally different from the numerical fluxes on the boundary facets, because in the boundary facets you have to account for boundary conditions. So instead of one function, our number of functions is multiplying. So we have to provide a numerical flux in the interior facets. We have to provide numerical fluxes on the boundary facets. Everything required to implement these terms automatically once the user provides the necessary details. Okay, so this is the numerical flux on the interior facets. This is the boundary flux. You define these things. Very easy to define, sitting inside Python. You don't have to go into the C++ setup inside in the NGStense if you don't want to. And then once you provide these functions, everything that's in the right hand side is known except for one quantity, and that's specific to tens. And so there is one extra routine that you would not need if you're just doing a DG method, and that is because of this nastiness here that came after the tens got mapped. So we can do time stepping with this. We can do time stepping with this because usually we make a mass matrix and you do time step with respect to a variable like this. But instead we have this. To go from this type of an equation to this type of an equation, we need the inverse map of this object. So you call this y, and then you need to go from u to y and vice versa. And so we have to provide this inverse map. Usually you just look at the flux. Do you know this flux? And you don't know this, but NGStense knows this. So assuming this is known, you just hand compute the inverse, extract the u, and then provide the expression. That's this inverse map function. Those are the things we need. So here is a simple example. This linear advection. It's a nice hyperbolic system. And then we'll go to a nonlinear example. And then I will be out of time. Okay, this is the object, conservation law object, which allows you to implement your own hyperbolic equations and experiment with tens. You do the tens lab like before, set up a mesh, and I think here is a nice little bump which we are transporting or advecting across the domain. And here is a prescription of the method. You first define f, that's just b times u. Then you say that you prescribe the numerical flux. Here is a simple upwind flux. If the b dot n is positive, do this, otherwise do this. It's upwind flux. Then what happens at the boundary? Well, some things are known on the boundary, the inflow boundary. So at the inflow boundary, you check which is the inflow boundary and provide the right data. And here is the inverse map. The inverse map is extracting u out of this expression, and grad phi is given by the tens lab object. So you just solve this algebraic equation and return it. That's the inverse map. Okay, and now we have a scheme, and there you saw how it got transported. Okay, not very exciting, but something simple to. If that doesn't work, then this doesn't work. The next one is burgers, which is a nonlinear example. Now, when we go to the nonlinear case, we need some more bells and whistles, because things may become unstable. It's not enough to just have a nice sufficiently many subtens and so forth. You need this viscosity of regularization or some analog of this. So we're using viscosity of regularization from this paper of German, Pescetti, and Popov. They say look at the hyperbolic conservation law, and where you have shocks, there is entropy is not conserved. There will be production of entropy. So you can compute an entropy residual numerically, and looking at the size of the entropy residual, you know which areas need regularization, and they are usually exactly where the shocks are. So we add some viscosity there, just exactly like what they do. They didn't do it in the context of tents, but Christoph has implemented this in the context of tents. Here's the entropy equation. You pick one entropy. There are usually many entropies. You pick one entropy, and then instead of the equality, you look at regions where you don't have the equality. You have something like the inequality, and that's the entropy residual. So, since the user is required to choose the entropy and the corresponding entropy flux, there's two more functions to be provided in the nonlinear case. You can omit them in the linear case. Nothing bad will happen. But in the nonlinear case, you can omit them, and usually something bad will happen. But you don't omit them, and you give that. And now, of course, you have to also discretize the entropy equation using dg. So there is a numerical entropy flux and the prescription for the viscosity coefficient. So a lot of things to prescribe. Let me just quickly go through this, because I don't have too much time. I have a minute or so. We put in all of these functions, which are all defined in Python, into the conservation law object, and then they ask the conservation law object to solve, given an initial condition. And it should show you a two-dimensional Burger's equation, kind of like a wave that's almost crashing. Okay, and if you did not see that, well, there's an animation that does it more, very slowly, very, very slowly.
What is this shock? There is a sudden change, right?
That was just a scale, visualization scale change. In the animation, you don't see that because we fixed the max and min. What is difficult is when it comes crashing. That's where usually things blow up, and it's not blowing up once you put the viscosity of regularization. And you can actually see, if you want to see how the entropy residual looks like, in the beginning there is no pattern to it, but later you'll see where there's a sharp transition, there's more and more entropy production, and that's exactly where the viscosity is being added. All right, that's all I have. Thank you.
Some questions or that?
Viscosity regularization outside this tent package, because I think it would be useful also in general.
I'm sure that German.
No, but in NGSolve.
In NGSolve. Oh, it's just adding Laplacian.
But the computation of the residual.
I don't know if there's an example with that.
You mean the form on paper or in NGSolve?
In NGSolve.
The same as on paper. I quickly saying it. Okay, yeah, another question.
Thank you. Okay, could you go back to your other notebook?
Yeah.
Like the last 1D example of your pitches?
This one?
No, the last 1D. 1D.
Yep.
So there are actually some points which depend on other points which are in the future. So.
Yeah.
So maybe, for example, this one
Yeah,
here.
I see that.
So
yeah.
this one depends on this point, but this point is in the future.
Yeah. So what happens is we solve. So the blue layer is solved first, then the green layer, then the red layer, then the blue layer. So this has already been solved. We don't care if it's in the future. It's already been solved. So we have data for.
It takes time for information travel from here to here. They take some time, so you have to move up in time here. But if you know the field here, then you can compute it on the whole cell.
Okay.
In other words, it has access to this information.
Thank you.
Okay, yeah.
Thanks for the influence count. Okay. So no other questions, and thank you,
All right.
Tenche, and for the speaker.